Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 6 Chemistry students. Welcome back. How are you? I'm very okay. I hope you're healthy and fine. I'm Alan, still with you in the chemistry lessons. We are still on topic of electrochemistry, that is Unit 12, electrochemical cells and their applications. We're heading in for lesson 3, which is about the electrochemical cell diagrams or the cell convention. Basically, cell diagram is about how can you draw the whole cell setup on a paper? How can you depict it on the paper? So, but before we look at today's lesson, let's take a quick checkup on the previous lesson content. That is lesson 2. We looked at how to measure the standard electrode potential, which we call E theta for half cells. The point of emphasis is simply get your half cell, which must be on the left-hand side connected to the half cell you want to determine its potential. In this case, this is the She and this is the copper. So the potential difference that would be set will be for that half cell, since we know that the She has a 0 value. So if we get anything above, then that value belongs to that half cell. That is what we looked at in the previous lesson. Then we also concluded by seeing the sign of the E theta relative to the She. What does a positive value and a negative value imply? Whereby we say the positive value implies that the She is losing electrons to that half cell. Example, copper, as you see the flow of electrons. But if you have a negative, the She is gaining electrons from that half cell. This is an example of zinc. But why negative? And here you see a positive. It is just simple. The She should be on the left-hand side where we have the oxidation. So this negative sign implies that the actual reaction taking place is the reverse of what is given to us, you see here. And why would it be given like this? It's because this value is measured relative to She, which has to be on the left-hand side, like for copper. So if you lose electrons to the She, you get a negative. If you gain electrons from the She, you get a positive. So this value and the setup should not confuse you. This setup is simply because zinc is losing electrons. But the value here being negative is because it's given as zinc gaining electron. It is the reverse of what is exactly happening. So that is what we looked at last time. We don't need to take much more time on that. So let's look at today's lesson content, which is the cell diagram. As usual, we must see what we are going to focus at, the key terms, and the objectives. So we're going to be focusing on the cell diagram and how to formulate it. Of course, we shall define it, what is a cell diagram and how to formulate it. Then we perform calculations involving standard cell EMF. We shall also, in that case, be looking at those two critical terms, that is cell diagram and the standard EMF. The reason why I give you key terms is for you to understand where the lesson is focused and take notice on the definitions and the work related to those key terms. That's why I give you those key terms. Then the lesson objectives, we should be able, by the end of the lesson, to deduce correctly the cell diagrams for all the setups and perform calculations accurately that involves standard cell EMF. So, what is a cell diagram? cell diagram. Simple. The agreed way of presenting cells on a paper. What do we mean? We mean you have your setup, is normally in a lab, but can you put it on a paper for someone who is not in the lab to understand what is happening? And that is what we call a cell diagram or cell convention. The agreed way. Who are those agreeing the way to do it? It was formulated first by the IUPAC, then once it has been agreed by that union, then it is done worldwide or in the scientific world. So a cell diagram is any agreed way of representing a cell on a paper. Let's take the example of hydrogen and zinc half cells when they are connected together, as you see it this way. How do I represent this cell on a paper without indicating all these? This is how it is represented. Platinum, salt, hydrogen gas, hydrogen cation, proton, then zinc cations and zinc salt. This implies, this single bar implies the change in the physical state. You see from a solid to a gas. You see here. This is the platinum. Gas comes in, the platinum absorbs it, and it loses electrons. Then the cations gain electrons. So we have platinum as a solid in connection, or it is connected to hydrogen as a gas, then hydrogen positive as in aqueous. So we have three physical states, solid, gas, and aqueous. This separates, that is the boundary in simple. Double bars represents the salt bridge, which is there to connect the two half cell, this and this. Then on the other side, we have zinc cations in connection with the zinc salt. Point to note in here, platinum is electrode, where the electrons are moving out or are moving in. Then zinc as a salt is also an electrode. So electrodes must come at the start and at the end of that cell. So this is the cell representation. One may wonder, why do we start with hydrogen electrode, yet it is on the right-hand side, or it is gaining electron from zinc? By convention, again, the She has to be on the left-hand side. And as such, in other words, this whole setup needs to be flipped or reversed this way. So we have the hydrogen on the oxidation side, then zinc on the reduction side. So what about if we have other cells without the standard hydrogen electrode? How would we represent them if we don't have a She? Example is that zinc and copper electrochemical cell. Can you give a guess? Yes. If we don't have a She, we said in presence of the She, it has to be on the left-hand side. So if you don't have the She, then you present them as usual. The half cell undergoing oxidation goes on the left-hand side. The half cell undergoing reduction goes on the right-hand side, as you see. This is the flow of electrons. So this is how you represent. If you are sure of the electrolyte, like zinc sulfate and copper sulfate, then you can add it. If you're not knowing what they are, then you can use cations. As simple as that. So in that case, that is how you can easily write the cell diagram. Some points to note in here. If you're given cells with their electrode potentials, you can tell which one will undergo oxidation and which one will undergo reduction by looking at that value. So a half cell with a more negative electrode potential will undergo oxidation. It will lose electrons. You can see zinc with copper. Then a half cell with a more positive value will, or less negative, will undergo reduction. We are going to be using this principle in the calculations. Of course, you may be asking, where do we apply such a kind of knowledge? Of course, we are looking at construction of cells, and I told you examples are the dry cells, the car battery, and so on. Those are the electrochemical cells. We know how to use a dry cell. So the emphasis is how does it really produce that electric current, or how does it produce that light that when you put it in a usual torch and you switch on, light is produced. How does it come about? So we are looking at the deep chemistry involved in that cell. So let's do a few components in here. The standard cell EMF. This is simply the difference, the electrode potential between two half cells connected. Like connect copper and zinc, you'll get a volt of 1.10 voltage. So that voltage is the difference in the potential of one cell and the other. Take a look here, the Duracell. This small Duracell, it has the potential of 1.5. I know we're going to look at the composition of this cell in details, but I'm showing you what this standard cell EMF implies. That potential value that you see, the 1.5 volts, it implies 1.5 volts is the potential difference created between one cell, half cell, and another. As I said, we shall go in details and look at this dry cell later on. So that is what we call by standard cell EMF. Simply connect the half cells, you will generate the potential difference. But if you don't have the materials to connect the half cells, then you can get the standard cell by calculation. The standard cell EMF is the value for reduction side and the potential for oxidation side. We have this example. This is a setup. When it is set up with a voltmeter, it will read. If you don't have this setup, but you have the potentials, you can actually get this standard cell EMF. How do we get it? By substituting these potentials. What do we see? Zinc reduction potential is minus 0.76. Copper reduction potential is positive 0.34. We know where these values come relative to the She. Can we substitute those values in the formula and we get the standard cell EMF? Yes, simple. Substitute the value for reduction and the value for oxidation. You will get this value. This minus, the way you see with the highlighter, is there to reverse the oxidation value. Why reverse it? As we started from the start, this value implies that this half cell, for instance, zinc, loses electrons. So it has a more negative potential. But the actual reaction is not zinc gaining electrons, but zinc losing. So we have to reverse this value to ensure that the reaction that is exactly happening is not gaining, but losing. That's why this minus is there, to reverse this side of oxidation. And you get your potential value. So basically, that is how you can make up calculations if you don't have a whole setup. So these are two ways. You either have a whole setup or do the calculation. A few guidelines as we do the practice question. As I said, they are always given as reduction potentials because they are in regard to She, which is expected to lose electrons. So you will always have it this way. But when you reverse this reaction, zinc cation gaining electrons to zinc salt, this value. If you reverse and make zinc lose electrons to zinc cations, even the sign reverses. That's a point you need to understand in here. And that is the point why this value is, this minus is added in. I think I'm very, very clear on that. Next, if you multiply by any factor, the potential does not change. We are going to see that in our practice question. It's because the potential of a half cell depends on the concentration of solution and the ionization energies. It is an intensive property. It is not depending on the stoichiometry or how the equation is balanced. We are going to be applying these guidelines. Let's try one practice question. Then we see how to do it. Then we can try other more questions. So we have that practice question. Let's go through it together. Practice question 1. What are we given? We are given aluminum and zinc. What do we have? We have aluminum. These are the reduction potentials. Given to us as 1.66 volts. Then zinc to zinc salt, its standard electrode potential is minus 0.76 volts. So we are to deduce the cell diagram or the cell conversion. So the first thought that should be in your head is, within these two cells, which one is undergoing oxidation, or which one is supposed to be set on the left-hand side? It will be aluminum half cell. Why? Because it has a more negative potential. This has a less negative potential. So the aluminum goes on the side of oxidation. And as such, we shall have the aluminum as a salt going to aluminum cations. We are reversing this. Then we put the salt bridge. We give zinc cations. They will gain electrons coming from zinc salt. So that is the cell conversion. Point to note, know which side is undergoing oxidation and which side will undergo reduction. Which side will lose electrons and which side will gain electrons. So that is, then we go to part B. Write balanced reactions for equations at each electrode. So if we look at the anode where we have oxidation, we expect aluminum to lose electrons to form aluminum 3 cations, and 3 electrons will be lost in there. So if you want to include the potentials, then this will be reversed. We shall have our E here becoming positive 166 voltage. I reverse this equation or this expression. Since it is reduction, gain of electrons, and it is a negative, so if you lose, it will become a positive. Next, let's look at the cathode. What happens at the cathode? We expect zinc to gain electrons. Gain of electrons to form zinc salt. So if we include the theta here, it will remain as negative 0.76 V. It's gaining electrons because it is connected to aluminum, which is more negative. So finally, we get the overall reaction equation. To get the overall reaction equation, we need to multiply to balance the number of electrons. The number of electrons lost here must be equal to the number of electrons gained here. So we must multiply by a 2 here. Then we must multiply by a 3 here. Why am I not including these potentials? These are intensive. This potential is an intensive property. It is not depending on the electrons in here, or the way we are going to balance it by multiplying a factor and a factor here. No. This depends on other factors intrinsic in the system. So the overall will be 2 aluminum as a salt plus 3 zinc cations, giving us 2 aluminum cations plus 3 zinc salt. So that's the overall equation. The electrons will cancel. This will make it up to 6. This will make it up to 6. Electrons gained equal to electrons. No, electrons lost here are the same electrons gained there. So if you are to get the E cell directly in here, you would add directly this value and this. We shall come back to it a little bit. Let's first use the usual understanding. Part C. Calculate the cell EMF, the E theta for the cell. As we looked at it, the theta for reduction minus E theta for oxidation. I'm using these words oxidation and reduction not to confuse you with left-hand side, right-hand side. Some people will confuse the presence of She and the absence of She and get it wrong. So the best is to use reduction side and oxidation side. So can we substitute in what has undergone reduction? Minus 0.76 volts minus 1.66 volts. Let's substitute in our calculator. Zero point 6 plus 6. We're getting positive 0.9 volts. So this is the electrode potential. This is the potential difference created. Let's now use this approach. Just simply add, because we've already considered this factor. Let's simply add. You will also get, if you add this, you will also get 0.9 volts. There is something I need to stress. There is something I need to be clearly understood on this part. When you're using this formula, simply substitute the value. Do you see this negative I'm putting in here? Yes. The presence of this negative and a negative, it will become a positive. So this side will be reversed. This side will be reversed, and the reverse is seen right here. The reverse is seen just right here. That's why on this part, the sign, I didn't include the sign because I've reversed what has been given to us. So when you add simply this, they will give you this value, and if you use this formula, you'll get the same value. Point to note, the formula substitute it the way it is with this a minus included, or this sign should be included. So that is it in terms of the calculations and determination of the potential difference for a cell. And in terms of the cell conversion, how do you depict a cell on a paper? That is the cell conversion. What are those signs imply? That is what they imply. So that is it for today, but as usual, I have to leave you with the exercise. I call it exercise 3. You notice each lesson, I have to leave you with the exercise. So you go through that exercise. We shall start from it in the next lesson. Thank you for your participation. Please calculate, go through all those exercises I leave you with for you to gain a much more deeper understanding of the concepts. Have a nice day, stay safe, and please follow the Ministry of Health regulations. I want to see you in the next lesson. Bye.